Reimann sums and areas are very closely related. When we were finding the areas, we had to have a function that was non-negative, and we defined a regular partition so that all of the delta x's were the same width. For Reimann sums, we don't need that caveat, and our partition has the only restriction is that b minus a over the partition has to be less than or equal to n. Now, the definition of a Reimann sum is let f be defined on a closed interval, a to b, and let delta be the partition such that a is equal to x naught, and x naught is less than x1, less than x2, etc. And it's less than xn, where xn is equal to b. Now, if delta x sub I is the width of the ith subinterval, and c sub I is any point in that interval, then the sum, as I goes from 1 to n, of f c sub I delta x sub I is called the Reimann sum. Now, let's look at an example. Suppose I want to evaluate the limit as n approaches infinity of the sum as I goes from 1 to n of f c sub I delta x sub I. So I want the limit of the Reimann sum for the function f of x is equal to the square root of x. I can use the regular definition, but it'll be a bit cumbersome. So instead of defining delta x sub I first, why don't I define c sub I, so that I'm going to pick a point in here, c sub I, that is equal to I squared over n squared. Now watch what happens when I do this. When I look at what f c sub I is, this is going to be the square root of I squared over n squared, or just I over n. Now you see if I start putting plus anything in there, this could get very ugly and it could easily become something that I wouldn't be able to work with. Well, I've defined c sub I, so now I need to define delta x sub I. Now what is delta x sub I going to be? Well, it's going to be let's define it from the center of my, not necessarily center, but from c sub I to c sub I minus 1. What is that width? Well, c sub I is I squared over n squared minus c sub I minus 1 is I minus 1 squared over n squared. And if I multiply that out and collect terms, it's 2I minus 1 over n. Now, let's go back to my function. I'm trying to find the limit as n approaches infinity of the sum as I goes from 1 to n of f c sub I delta x sub I. So this is the limit as n approaches infinity of the sum as I goes from 1 to n. Now I'm going to color code these because it can get a little confusing. f c sub I is I over n times delta x sub I, which is 2I minus 1 over n. Now, I'm just going to go to a normal color here. This is the limit as n approaches infinity. And did I forget my square? I don't know why I always drop my square there. You have to be careful when you do these. So I'm going to factor this n cubed out of the denominator. And then I'm going to sum as I goes from 1 to n of, now this is 2I squared minus I. Remember, I can factor the n cubed out of the sum because I'm not summing over n, but I can't factor it out of the limit. So this is the limit as n approaches infinity of 1 over n cubed times. Now what are these sums? Well, this is 2 times n plus 1 times 2n plus 1 all over 6 minus the sum of I, which is n plus 1 over 2. This now becomes, let me extend my page here, I'm running out of room. It becomes the limit as n approaches infinity of, when I multiply this out, I get in the numerator 4n cubed plus 3n squared minus n all over 6n cubed. And when I do this, that one goes to 0, 0. This goes to 4/3, or 4/6. Sorry about that. Let me erase that. Goes to 4/6. We look at the coefficients, or 2/3. Now, in a previous problem, we found that the area of x equals y squared, between x equals y squared and the x-axis, we found this area was 1/3. Another way to write this function is y is the square root of x. We just found this area is 2/3. And we know that the area of the square from 0, 1 to 1, 0 here is 2/3 plus 1/3 is 1.